This is lecture 7. So far in lectures 5 and 6, we established a procedure for nodal analysis for circuits, DC circuits that do not have voltage sources. In my view, it is probably the most important series of lectures in the course because nodal analysis remains the most powerful circuit analysis method we have. And it is one that if students find some measures of fluency of essentially in that procedure right now, it carries really throughout the end of the semester. So I strongly encourage students to try to get some problems under their belt. And how many problems depend on the students? I tell students somewhere between 3 and 6 or 7 problems that you've done, not that you're watching the solutions, but that you are doing in terms of taking a circuit you haven't seen and finding the node voltages. So today, we essentially going to be able to deal with generalized circuits. That is, we're going to include voltage sources. The way I want you to see this particular lecture is an overlay on the lecture that we've had before, particularly lecture 5, where we covered nodal analysis for circuits, for DC circuits without voltage sources. So think about it as an overlay. In other words, I want to specifically treat how do we deal with voltage sources when we have them in the circuit. Okay, there's special treatment we will do here. And then we're going to finish another mini lecture by doing an example in which I'm going to do it on paper using the document camera so that you see my thinking in terms of when you get a problem. So let's share screen here and let's begin. So again, we're looking at an overlay. We're looking at adding pieces, namely how to treat voltage sources. So the first thing we do, just like we did for circuit without voltage sources, we identify all the nodes in the circuit. And we spend some time talking about doing so correctly because nodal analysis is based on nodes. So if you don't get the nodes correctly, most likely everything else is not correct. We're going to identify all the nodes, and then we're going to select an arbitrary reference node. So these are the 2 steps that we were doing before. Nothing changes there. The next thing we do also is we label the other nodes, V1, V2, and they are the unknowns. If you remember in nodal analysis, the number of nodes, let's assume the number of nodes is n. The number of unknowns is n minus 1, which are the node voltages, because we assume the reference node is known, and we say it's easier to assume that it's 0 volt. At this point, I want you to think when you get a circuit that has voltage sources, I want you to identify the voltage sources. So I'm showing you the 2 voltage sources that we typically can get. You either can get an independent voltage source in the case of the 2 volt here, or you can get a dependent voltage source in the case of the 3IA. Remember, voltage sources needs to have plus and minus in their symbol because it essentially establishes a potential difference between the plus and the minus. The difference between a dependent and an independent source is that the dependent depends on something else, whereas the dependent source is like your car battery. It establishes, say, 12 volt between the red and the black terminal, which are the nodes. Okay. So one step I'm going to ask you again, we're going to cover these procedures, but when we do example, that's when they're going to become more real. They're going to be grounded, if you will, in how to do this. And then obviously when you do example is when you develop some proficiency in the method. So we're going to form what's called supernode. Think of supernode as a blob around the voltage source. A blob, just like I'm drawing here essentially with the orange. I'm doing that on both cases here. So key things to realize, supernodes can only have sources and nodes in them. Nothing else. Sources, and I mean, sorry, voltage sources and nodes, nothing else. Never find a current source in a supernode, never find a resistor in a supernode, okay? Only voltage sources and nodes, just like I'm showing. So I just want you to draw a blob around the supernode. What we're going to be calling supernode, by the way, does not eliminate the node. You can still see I have V1 and V2, and in the case of the dependent source, V3 and V4 still exist, okay? So that's the first thing we do. In the case when we have 2 voltage sources that share a common node, And I don't mean that it's in series or in parallel. I'm just saying share a common node. In the case of the node that I'm pointing to, we're going to combine those supernodes into a larger supernode. Okay, so when we have two supernodes or more that share one common node, we're going to combine the supernode into a larger supernode. Okay, that's kind of the two rules that we're going to do here. We draw a supernode about the voltage, each voltage source, and then we combine them if they share a common node. Nothing to do with series and in parallel. The next thing we do, we write a KVL, a Kirchhoff voltage law for each source. I'm going to affectionately call it the source equation. Okay, so in essence, what is a voltage source? If you think of your car battery, it maintains 12 volt, or it attempts to maintain 12 volt between the terminal A, the red terminal, and the black terminal. So the voltage source definition is to trying to maintain a voltage difference between the two terminal or the two nodes. So in essence, the source equation is writing what the voltage source does, and we do one equation per voltage source. In the case of the independent source, we have where the pluses, V1, the node where the pluses, minus the node where the minuses, minus V2 equal 2 volt. So these are the easiest equation to write. So in many respects, when you have voltage sources, the equations are very simple to write because they maintain a potential difference between the plus and the minus, a given potential difference. In the case of the dependent source, it is V3 where the plus is minus V4 where the minus equal the value of the source, which is 3IA. Okay, so those are two equations that are easily written if we had these two voltage sources in the circuit. Okay. The rest of the problem, somewhat similar. So the next step, we're going to apply KCL. We're going to apply KCL at each node that is not the reference node and doesn't belong to a supernode. In fact, many times I'm going to actually talk about what's called a regular node. And I'm going to ask you, do we have a regular node in the circuit? I'm going to define a regular node as a node that is not the reference node and is not connected to a voltage source. So we're going to define it as a regular node. And the reason I'm doing that so that we can apply KCL, this is the kind of nodes we had before. We apply KCL at each of those nodes, okay? So that's a similar step we had before. We did that before. This step here, the last step, is different. We didn't have supernode before. We're going to apply KCL at about the supernode. You know, again, we're not eliminating nodes. We're just looking at current coming into a larger area and current leaving. We're going to apply the KCL at each supernode when the reference node is not inside the supernode. Okay, and we're going to practice this and show you the examples of that. All right, so we're going to apply KCL at a supernode that doesn't have the reference node in it. Okay. The rest of the problem is fairly similar to what we're doing. We use Ohm's law to write the resistor currents in terms of node voltages, passive sign convention, and then we substitute the Ohm's law into the KCL equations, and then we get 3 equations, 3 unknown, 4 equations, 4 unknown, and we solve the system of equations for the node voltages. Remember that for node analysis, the node voltages are the unknown. No matter what I ask you, you first find the node voltages, and then you can answer the questions like power, current, voltage, and things of that sort. Okay, so I'm going to practice 2 problems, and then I'm going to ask you to do one a little bit later. So that we put things in practice here. So I've prepared the circuit for you here. All right, so I've skipped the preparation step. What do I mean preparation step? Identifying the node. You have all the nodes identified, and then I select the reference node at the bottom. And then I label the node V1, V2, and V3. The only thing that's left here, I haven't put current on my resistors. Now, keep in mind here, I'm giving you admittances. Anytime you see S for resistance, I'm giving you admittances just to make the calculation a little bit easier. So the admittance is given, the resistance is 1 over those values for each resistor, okay? And this particular problem is asking, let's find the node voltages. So how many nodes we have? We have 4 nodes. How many unknowns we have? We have 3 unknowns, V1, V2, and V3. The next question I'm going to be asking you from now on, how many voltage sources we have? And you should answer 1 here. We have 1 voltage source, and it's that 4 volt. Okay, because what I'm going to do essentially, I'm going to do a super node right here about that voltage source. Okay, and I'm going to realize, well, when I do the super node about the voltage source, about the voltage source, that does not contain, none of the node is the reference node. The reference node is at the bottom. So this is the case where the super node does not contain the reference node. Okay, so these are the kind of things I'm going to ask you over and over again to develop some muscle memory in terms of how you solve these circuits. Okay, so let's go about this and see. And then I'll do another example of this. So the next thing I do, I put current on my resistors. Again, the direction of these currents is totally arbitrary, but once you put a current, that determines what the plus minus is, even though we're no longer showing that here. So first thing I do, I am in the practice of writing the voltage source equation first, because I tell students that's the easiest equation you have. What the plus is for the voltage source minus what the minus is equal to the value of the source. So in this case, V3 minus V2 equal 4 volt. So this is the easiest equation you're going to write. You don't have anything to do after that with it. It's actually done. Okay, it's one equation for your 3 unknowns. Okay, the next question that I would ask for this particular problem here, do we have regular nodes here? Remember how I'm defining regular nodes? It's a node that is not the reference node and not connected to a voltage source. Yes, we do have a regular node. It's node V1. So I can do a KCL at node V1. Okay, I can do a KCL at node V1 just like regularly before, right? So current coming in equal current coming out. What's coming in? I have I4 coming in to the node V1. What's leaving? I1 leaving, 6 amp leaving. So you have I4 equal I1 plus 6. Okay, so this is my second equation. Again, the second equation in terms of current, I'm going to have to do Ohm's law to get it in terms of node voltages. The last step in this is a case where the supernode, which I call SN here, supernode in orange, does not have the reference node. So we do KCL about the supernode. We're essentially looking at what currents are coming into that supernode, what current leaving that supernode. Okay, just like that. And I'm going to give you an explanation here, but just so that we make sure what's currents coming in. I have I1 coming in, and then I have I2 leaving, I3 leaving, and I4. So the equation is I1 equal I2 plus I3 plus I4. So I'll give you a reason why we have to do this special treatment. First of all, because the voltage source, what a voltage source does is maintain the potential difference across the plus and the minus. So we need to essentially put that in an equation, which is what we did for the source equation. The second part, we do not know the current that's under 4 volt. So if we had done a KCL at node V2 or at node V3, we would have the current that's on the source, and it's not 0. Otherwise, the source would be dead, but we don't have Ohm's law for the voltage source. So we actually do a KCL around the whole supernode, and then we use the relationship that the source provides between the terminal to then solve the problems. Okay, so I hope that makes sense. So this is the KCL about that supernode. Just a note here, when we draw a supernode, we're not getting rid of any node. The supernode is not really a node. It's an area, a larger area over which I'm going to do KCL. The rest is similar than what we're doing. Ohm's law, again, remember I'm providing you Siemens value. So the current is voltage multiplied by the admittance as opposed to voltage divided by the resistance. That's what you see the multiplication here. So anytime we're writing Ohm's law, we're looking at passive sign convention. So for example, I4, the fact that I4, I put it going from right to left, so my plus is here, my negative is here. Okay, so I4 is V3 minus V1 divided by the resistance or multiplied by 2. Okay, and similar thing for I1, I2, and I3. So we take these 4 Ohm's law equations, we put them into the 2 KCL, we collect terms, because we have another equation, which is V3 minus V2 equal 4 volt. So that gives us the 3 equations, the 3 unknown, that we can solve for V1, V2, and V3. Okay, so this is our first example. This is a basic example, but it shows you an example of a circuit that has a supernode in which I'd put the reference node outside the supernode. So it gives you one example. The next one, I'm going to essentially do something slightly different so that you see. So I hope that makes sense. Okay. Let's go now to look at the second case. And the reason this case is interesting, because it's going to have one of those combination supernode. We're going to combine. So let me see. So I'm putting a dependent source here. So how many voltage sources I have? Clearly, this is a voltage source here. This is another voltage source. So I have two voltage sources here. So when you're doing nodal, I'm going to ask you to identify the voltage source right off the bat, because special treatment's going to be taken. It's going to be needed to deal with the voltage source here. Here too, I'm dealing with Siemens. So just notice that I'm providing you admittances, not resistances, just to make the calculation easy. Okay. So I'm going to prepare the circuit. Let me clean up a bit here. I'm going to prepare the circuit. So I'm going to find a node. There is one node here. There is another node here. There is a big node bottom here. Okay. There is a node here. And there is a node here. So what do I have here? I have 1, 2, 3. I have 5 nodes. So I'm going to have 4 knowns for the circuit. So this is the kind of things I want you to get very familiar. And you only get there by doing problems. 5 nodes in the circuit, 4 unknown. So let me show you the circuit prepared. Okay. So I'm putting the reference node at the bottom. I've labeled the other nodes, V1, V2, V3, and V4. And then I created a supernode, but that supernode has a common node here. That's the common node. So I combine these two supernodes into a larger supernode. Okay, so there are several steps here that I want to show you again. The first thing, let me go back here. Let me just clean up a little bit, just to make sure that things are clean up here. Okay, so I'm going to have a supernode here for this source. Okay, because that's a voltage source. I'm going to have a supernode here for this voltage source. Okay, so those are the two supernodes that I have. And then I'm going to realize that they share that common node. So I'm going to combine these two supernodes into a larger supernode, which is what we have. I hope that makes sense. So we're going to need to practice this a little bit more. And you get this. Okay. And what makes it also a different problem than what we did first is that this is the case where the reference node is one of the nodes inside of the supernode. Okay, so we're not going to do KCL about the supernode. Okay, so we're going to need, this is going to need a little bit of practice to get there. So the first thing I want you to think though, how many sources you have, how many voltage sources you have here? And I'm hoping you tell me 2. So you need 2 source equations. Okay. So again, the supernode is merely an area that we extend. So these are the 2 source equations here. For the independent source, I have V1 minus 0, what the reference node is, equals 6 volt. So V1 is equal to 6 volt. And for the dependent voltage source, I have 0, where the reference node is, minus V3 equal to VA. Okay. And the given VA was given in the problem. Given the way I select my reference node, VA is simply V2 minus 0. So VA is actually V2. So right there, very quickly, without a whole lot of work, I actually have 2 equations for my 4 unknown. Okay. So again, if you look at, let me just go back here for a second quickly. If you look at the original problem here, just go back. Let me just clean that up here. This is the problem. This is a problem that was given. The dependent source here had a voltage 2 VA, where VA was given essentially as the potential across the 2 Siemens resistor. Okay, so that's what we have here. So we prepared the circuit. We realized that those 2 supernodes had a common node at the bottom. So we combined the 2 supernodes. Okay. Again, I want to make sure this note here that I speak a little bit to it. even though I mentioned that before, the super node is not getting rid of any node, is merely looking at KCL around a larger area around the voltage source, because we don't know the current to the source, and there is no Ohm's law for the current for the voltage source. Right? So we find a way to use the relationship between the terminals at the voltage source and force, and then we look at the KCL around it. So only voltage source should ever be, voltage source and node should ever be in a supernode. You should never find a current source or a resistor in a supernode. So we did the two source equations, one for the 6 volt, where the plus is minus where the minus is, equals 6 volt. And then one for the dependent source, where the plus is, which is 0, minus where the minus is, which is V3. So minus V3 equal to VA. And we furthermore recognize that VA, which was given in the problem, being the potential across the 2S resistor, it's V2 minus 0. So we basically get two equations for a toroid node. Where are the next two equations are going to come from? I'm going to ask you, do we have a regular node here or one or more regular nodes? And I define regular nodes as a node that is not the reference node and not connected to a voltage source. You should be able to identify V2 and V4 as two regular nodes. So we're going to do KCL at no KCL about the supernode because it has a reference node, but we do KCL at node V2. Current coming in equal current coming out. So I1 coming in, I3 and I2 leaving. And we do KCL at node V4, which I2 coming in, I5 coming in, and I3 coming in. So all of them sum up to 0. Again, no KCL about the supernode. No KCL about the supernode because this is a case where the reference node is inside the supernode. The rest of the problem is pretty similar with Ohm's law for the current on the resistors, paying attention to the passive sign convention and noting that I'm providing you admittances. So it's current equal voltage divided by resistance or current equal voltage multiplied by admittance. So that's why you see the multiply by the admittance of each resistor. We take those 5 Ohm's law equations, we bring them into the KCL equations, collect terms, and then we find ourselves with this set of equations, and we can calculate V2, V3, and V4 because V1 is known, it's equal to 6 volt. Okay, so that's the essence of this problem. This is a more complicated problem. It had more than one voltage source. It had supernode that needed to be combined. And on top of that, this is a case where I put the reference node inside the supernode, so no KCL about that supernode. So these are what's different from what we've done before. Each problem is going to be different. In many respects, it is your choice where you put the supernode. I'm sorry, your choice where you put the reference node, not the supernode. The supernode is going to be fixed by the problem. Your choice where you put the reference node. So I could have put the reference node where V2 is. So again, different problem, different approaches here. Okay. So I'm going to go here. So what I want to do next, I want to put a problem for you. I want to put a problem for you to essentially solve. This problem is obviously asking you to calculate power for each element. Power for the resistor, for each resistor, absorbed by each resistor, and power that's from each source. So that's it. But the underlying problem, anytime I ask you anything, if you're doing nodal analysis, I'm basically asking you to calculate the node voltages. Okay, so let's focus on how to do the node voltages, and then we'll deal with power at the back end. So I want you to pause this video or stop it and give yourself 25 minutes to calculate the node voltages. You can answer the power questions after. Okay. So I'm going to again pause, and I'm hoping you either pause or stop. And then I'm going to do the problem on paper so that you have a feel for how to do this. So we're going to do something a little bit interesting today. You can see that I put the circuit, I put two versions of the circuit here, one on the left, one on the right. What I'm going to do essentially, I'm going to select a different reference node and show you how the solution maps out as I do that. I want you to have a feel for what we're doing here, you know, as we select the arbitrary reference node, what is the impact on the solutions? Okay, so on the left here, So let me go here and I'm going to put, where are my nodes here? These are my nodes. These are my nodes here. This is my node, one other node here, and another node here. Okay. But what I'm going to do, I'm going to put the reference node right here. Okay. On the left. And then I'm going to label one V1, V2, V3. Okay. So that's what we're going to do here. So that means I have a 3 unknown problem, and then I'm going to put current here. I1, I2, I3, I4, I5. Okay. So this is essentially preparing the circuit for solution. One last thing that I'm going to do here, I'm going to ask how many voltage sources we have in this problem, and I'm hoping you answer me 1 voltage source. Okay, it is the 5 volt. Then I'm going to do a super node around that voltage source here in green. Okay, so I have prepared the circuit for solution. You don't see my green too well, but you see my dashed line around the voltage source. That is my supernode. This is the case where the supernode does not have the reference node. Okay, so I have 3 unknowns. I need 3 equations. Again, I'm going to sketch the problem. I'm not going to solve them completely, and then we'll go back to the PowerPoint. I want you to see how that pans out depending on different selection of reference node. So first thing I'm going to write here, it's my source equation for the voltage source. I have 1 voltage source, so I'm going to write 1 source equation, which will be V2 minus V3 equal 5. This equation is actually done. I don't have to do anything with it. It's a completely done equation. It's an easy equation to write. Where the plus is, the node where the plus is, minus the node where the minus is equal the value of the voltage source. We don't write this for current source. As you can see, I have a 5 amp current source. We don't do that. Okay, we write it only for voltage sources. And then I'm going to ask you, do we have a regular node? We do. It is node V1. That is a node that is not the reference node and is not connected to a voltage source. And this is the case where we will do a KCL about the supernode because the supernode does not have the reference node. So let me write the 2 KCL equations. KCL at V1. Current coming in equal current coming out. So I have 5 coming in. And what's coming out? No, I got 5 and I get I2. 5 plus I2. 5 plus I2 coming in, and then I1 coming out, plus I5. Let's call equation 1, because that equation is pretty much done. So 5 coming in, I2 coming in, again, depending on how I put my current, and equal to I5 plus I2. Then I'm going to do KCL at supernode does not have the reference. Okay, so KCL at supernode because it doesn't have the reference. So let me look at current coming in equal current coming out. So that means I4 coming in plus I1. And then what's coming out? I get I2 plus I3. So that's equation 2. So these are my main equations for my 3 unknown. I got the source equation, which is an easy one. It's a done equation. Then I write 2 KCL equation, one at regular node V1, and then one at the supernode, because this is a case where the supernode does not have the reference node. Okay. And then I do Ohm's law. So in this particular case, I have I1 equal V1 minus V3 over 5. I2, where is I2? I2 is V2 minus V1 over 2. I3 is V2 minus 0 over 10. I4 is 0 minus V3 over 4. I5 is V1 over 1. Okay. So these are my Ohm's law. I purposely putting 0 minus V3 so that you can see how I get minus V3 over 4. Okay, so these are my Ohm's law equation. These are the steps that I expect to see from your work. All right, I'm going to use this Ohm's law equation into the two KCL equations. So one becomes 5 plus I2 plus V2 minus V1 over 2 equal I1 V1 minus V3 over 5 plus I5 plus V1. I can multiply by 10. So what do we have? We have 50 plus 5V2 minus 5V1 equal 2V1 minus 2V3 plus 10V1. So end result is 50 equal, I can send everything on the other side. So this is 12, so 17V1 minus 5V2 minus 2V3. So that's the second equation that I have. And I apologize because my document camera crashed. So I am going to bring it back up. And so my apologies because my document camera, so you get a chance to at least see where I am up to this point. Just a little bit of a backup here. I essentially use the Ohm's law equations into the KCL at node V1. And then I put them in the same denominator by multiplying by 10. That's what I do here. I multiply by 10. Okay. And then collect terms and I get that equation here. Equation 2. If I do the same thing here, what do we have? I4, which is minus V3 over 4 plus V1 minus V3 over 5. I4 plus I1. Okay. And that's equal to I2 V2 minus V1 over 2 plus I3 plus V2 over 10. Okay. I can multiply this equation by, we can multiply by 20. If I multiply the whole equation by 20, what do we have? Minus 5V3 plus 4V1 minus 4V3 equal 10V2 minus 10V1 plus 2V2. All right. And then I can send everything on I can send everything to the left and then collect terms. So so we got 14V1, and then we have minus 12V2 minus 9V3 equal to 0. So this is my equation, is my third equation here. This, and this are the three equations that we need to solve for V1, V2, and V3. I'm eventually going to go back to the PowerPoint and show you, but I wanted to show you the handwritten version because that is the work that I want to see either on your quiz or on your exam. And I hope it makes sense that we do that. So I'm going to take that problem now, and then I'm going to essentially do the same problem, but instead of selecting this node as the reference node, so let's put some notes here. The nodes are the same. I'm going to select this one as the reference node. So I'm going to essentially say V1, V2, V3. Okay. And then, of course, we have a supernode here. Right there. That's my supernode. And you should at least note in this particular case, the supernode has the reference node. And then I go ahead and put my currents. I'll put the same way I had. I1 here, I4. I'll put them the same way. I3, I5, I2. Okay. Of course, this particular problem will be different because my nodes are different. So the node values will be different, but the power or the voltage difference will be the same, and the power for the element will be the same. So key things to notice here, no KCL at the supernode. It has the reference node.